So I wanted to clarify some of the proof elements of the example that we did yesterday in class. So let me start by writing down some helpful information about the image and the pre-image through a function. So the image of a set A under a function f is defined to be all of the f of x's, the elements of the range, that come from elements of A. And so what I can say about elements of this image set is the following. If you are looking at an element y of this set, so I'm changing the variable from x to y because x is acting like an element of the domain, whereas the elements of the set are elements of the codomain or the range. So I'll use the character y for this. I mean, what this means, if you have an element of f of a, this means that y must be f of x for some x in a. So I can write that in math like this. There exists some x in a such that y equals f of x. So this will be a useful observation when we're actually using this set within the proof, because it's not like we just want to know what the set is defined to be. We actually like to make statements about elements of that set. So this prep will be useful. And I want to do the same thing for the inverse image of a subset of the codomain. I'll just switch up the letters. It may help us distinguish these objects in our minds. So it's understood that A is a subset of the domain, whereas B is a subset of the codomain. So this is going to be a collection of x values in the domain such that f of x lands in B. And again, I want to make a useful translation about elements of this set. So the elements I would likely call x because they're understood to be elements of the domain. And what it means for x to be an element of the inverse image of A is that f of x lands in B. Okay, so now let me run through the proofs of the statements that we were working with yesterday. So statement number 1 is that if f happens, I'll use lowercase f here because that's what I always end up doing anyway, but so if a function from x to y happens to be 1-to-1, so that just means that no two different elements of the domain get sent to the same element of the range, then, also I have to take a subset of the domain. So if f is 1-to-1 and A is a subset of the domain, then we'll prove that f inverse, the inverse image of f of a is equal to A. So the inverse image of this set, which happens to be the image of A, is equal to A. And since there's two things that we mentioned yesterday. This is a conditional statement, if then, so we're going to prove it directly. And also the part that we're trying to prove is a set equality. So we're going to use a so-called point chase argument to do so. So I'm going to go ahead and let f be 1-to-1 and A be a subset of the domain. Now my task is to prove this right here. So as we sort of outlined yesterday, we do this in two directions. We first prove that this set is a subset of the right set, and then the right set is a subset of the left set. So let's go ahead and let x be an element of the left set, and it's reasonable to name the element that I'm taking as x rather than y, because I understand that pre-images or inverse images are subsets of the domain. So I let x be in there, and I'm going to try and glance up here to help me translate what that means. So I've got an x and an inverse image of something. So let me underline that something and understand up here, oh goodness, I've realized that I've put the wrong letter there. Sorry about that. There. So B was the set that I was using here. And the reason that I did that is I didn't want to conflate it with A. Okay, anyway, so X is in the inverse image of this set that I'm underlining in red. That red set is acting like B, all right? And so I can just literally translate this now. X being in the inverse image of this red set means f of x is in the red set. So my conclusion, my first conclusion that I want to make in this proof is that f of x is in f of a. Okay, and I like to get a picture drawn here. Here's the domain x, and I'm focusing my attention on an element of the domain that happens to have its corresponding function value inside of the set f of a. That's where I'm at in the proof. So I know this is f of a here. So what I've concluded so far is that f of x is in the set f of a. And it's at this stage that I have to translate this carefully using the first observation up here so that I don't I don't miss the fact that one-to-oneness is very, very important here. I can't cancel the f's, as I said in class yesterday. We'll see, like the last part of the exercise that we did yesterday, we justified that there's no way I can just cancel f's here without invoking the fact that f is one-to-one in some way. Because in fact, it's not always the case that when f of x is in f of a, that x has to be in a. So anyway, so let's carefully translate using this observation above what I've just discovered. Okay, so I have an element in f of a. What does that mean? Well, if you're an element of f of a, then this happens to be true over here. There exists some x in a such that y equals f of x. Now I got to be careful because this existence here is dependent on the y, of course, and I've already used the variable x in my proof so far. So I can't reuse that variable when I invoked this existence. So I have to use a different letter. In class, I think we use z, so let's go ahead and write that down. So there is some z in a such that the y that I'm looking at, that's f of x equals f of that x value, f of z in this case. So that's the best I can do. All I can say now in my drawing is that there's some z that gets mapped to f of x. That's what it means for this dot right here to be in f of a. Something in a gets sent to f of x. But I'm not sure yet that x and z are the same thing. Okay, but this is perfectly set up to invoke one-to-oneness now. So since f actually is one-to-one, I know that the image of x and z being the same is equivalent to x and z being the same. Since f is one-to-one, we have that x equals z. And then I sort of remind myself where I'm headed. I'm in the middle of trying to prove this set is a subset of this set. I took an element of the left set, and I'm hoping the punchline is that that element ends up being an element of A. But I do have those pieces. I just need to put them together. So z is in A, and x is equal to z. Hence, x is in A. Okay, so that part of the proof is done. You can summarize what you've just proven, that this is a subset of that, but since it's labeled anyway, it would be a bit redundant to do that. Okay, now we're going to go ahead and do the other direction of the proof. And as I noted in class, this half of the proof uses the fact that f is one-to-one. In order for this set to be a subset of A, it actually is required that f is one-to-one. The other direction, as it turns out, does not rely on f being 1 to 1. In fact, for any function, a is going to be a subset of f inverse f of a. So because of that, the nature of the proof, it just flows quite differently because it happens to be a sort of a weaker statement that's true in general. Okay, so I'm going to let x be an a, and then I'm hoping to get that x is in this set over here. So I am sort of working backwards in some sense. I'm still going to be glancing up here and looking at those translations. I'm going to say, well, what would it take for f inverse, what would it take for x to be in f inverse of something? And I look over here and see what it takes, this characterization. And then same thing with the f of a. Okay, so look, just consider f of x. F of x, here I'll get a new picture drawn. F of x is an element of the codomain. In fact, it's an element of the range. So it's a perfectly good y value, if you will. It is a member of the codomain. And look, we know that, if I call that element of the codomain y, then that element satisfies what it takes to be in f of a. Let's look at what it takes. In order to be an element of f of a, there needs to be some x such that y equals f of x. So this y value here, f of x, satisfies the condition to be in f of a. So the conclusion that I make from here is that this thing, so f of x, you can call it y if you want, but it's not necessary. So f of x is a y value that satisfies this condition. F of x is in f of a. So, the drawing that I might have going over here is I selected an x element that was in the set A, and by definition of f of a, f of x is definitely in there. F of a is exactly the f of x's for x in a. I have an x in a, so f of x is by definition in f of a. Okay, and now I want to look at where I'm headed. What would it take to get x in f inverse of something, all right? I really want x to be an f inverse of f of a, so I gotta inspect carefully what that would mean. X is going to be an f inverse of something, and the something here I want to be f of a, as long as f of x is in that something. So let me mark the somethings here. So right here, this is acting like the b, and let me pick another color. This right here, f of x is in that b, is satisfied. Look, f of x is in f of b. Oops, I'm circling the wrong. Oh, sorry, b. b. F of a is standing like b. Okay, so f of x is in b. F of a is standing for b. Okay, so these two things are synonymous. So the conclusion that I can make from this is that x is in f inverse of the red set. F inverse of b up here, f of a is standing for b. So that ends up being, I'll just make a conclusion at the very end. I've done both directions of the subset argument. Oops, sorry, I'm not paying attention. So what I'm concluding is, since the left is a subset of right, right is a subset of left, I've proven that the two sets are equal. Okay, I hope that clarifies a little bit what was going on with how we were invoking these statements up here. I know it's a little bit subtle, but I think maybe this preparatory work is helpful. Let me go ahead and do the same thing for statement number 2. Again, we have, a conditional statement whose punchline is set equality, so the outline of the proof is the same as the previous exercise. Okay, so where do we start? We want to start by selecting an arbitrary element of the set on the left, and I'm naming that element y because I understand that an element of the image of a set lies in the range of the function. So this is where I start, and then I can scroll up and remind myself what it means for something to be an element of the image of a set. It means that there is some member of the set A such that y equals f of x. So I'm using that translation. Okay, there we go. And oops, I didn't mean to say A, right? The image set that I'm looking at it's the image of A1 intersects A2. I was looking up above too much. Okay, so there is some member of this set such that f of x equals y. Okay, let me translate what it means for x to be in A1 intersect A2. Just by definition, it means that x is in A1 and x is in A2. And now I can glance up here again and say that y being f of something that is in A1 means that y is in f of A1. And I can invoke the exact same thing for A2. So let me mark these color here. So first, observing the definition of being in the image of A1 is completely satisfied by this blue thing right here. So by the blue, hence we have that y is in f of A1. Similarly, y is in f of A2 by putting together this observation and this observation. And by definition of and, so hence y is in there and y is in there, we have y is in the intersection of those two images. Okay, notice that one-to-one was not used there. I mean, that observation is true in general, and it turns out that one-to-oneness is only used in the other direction. Okay, for the other direction, let's let y be in the image of A1 intersect image of A2. Translate that subset. What does it mean? Or pardon me, intersection. What does it mean? It means that y is in f of A1 and y is in f of A2. I glance up here and I remember what it means for y to be in the image of a set, and I need to invoke those two things separately. So y is in FA1 means there exists some x, blah, blah, blah. Y is in FA2 means there exists some x, blah, blah, blah. But I had to be careful because I can't use the same variable when I invoke those two things separately. So this is what I'll choose to say. Hence, there is x1 in A1 such that y equals fx1, and there is some x2 in A2 such that y equals fx2. You cannot assume that these are the same thing right now. I mean, if you do, then you have proven this subset direction for an arbitrary function that's not even one-to-one. And we simply know that it's not true in general. So that would be the common mistake, is to accidentally assume that these are the same thing. Okay, so what do I have right now? Y is this and y is that, so they must be equal to each other. And since now f is 1-to-1, we have what we want, that x1 is equal to x2. So since f is 1-to-1, we have x1 equals x2. And just to, like, since I know that they're the same number, I'm just going to, like, rename. This is not necessary, but it just makes the punchline a little bit cleaner looking. So I'm going to call x1 and x2, just call it x. And then what I want to say is now that note that and this is just by glancing above, x2 is an A2, x1 is an A1, but they're the same number. They're both x. So note that the number x, or the element x, is in A1, intersect A2. And so now I just piece this together. So I have that x is in A1 and A2, and I should probably, just to be explicitly clear, y equals f of x here, because y is simultaneously f of x1 and f of x2. So I have that x is in A1 and A2, and y equals f of that x. So by definition, we have that y is in f of A1 intersect A2. Oh, well, I'll make a conclusion. So f of A1 intersect A2 is indeed equal to FA1 intersect FA2. Okay, I hope that little clarification helps. Let me know if you have any further questions about it.